Hello, my name is Dylan Elliott. I will be looking into a project called CPPYY, primarily for eliminating the garbage compiler. Now, if I seem a little stuffy, that's because I'm a little sick. But moving on. I looked into CPPYY for, well, a couple of reasons. One is that it compiles into a pre-optimized state, namely O2 compiled, which should be sufficient optimization. But once you've compiled it, you just put your C code into a few points and run your script. It is literally that retarded simple, and I don't mean that to be disrespectful to retarded people. Now, when I first looked at this project, or was looking for something like this, I have never, when looking at code, ever, including interpreters, have found something quite like this project. Blew my mind that a option like this existed, where you could embed cling into Python. One, I would think that would be next to impossible because there's theoretically no functional way one or any large group theoretically could comprise most, if not all, of C into a few sets of frameworks that interface to each other in Python. Blew my mind this existed. Because I thought I would just have to manually rewrite the whole of Python inside cling the interpreter itself. But no, somebody decided to port the whole thing, C++ and C, all in, so that it can just read your code and execute it. No additional linking step, no under the hood showing you where it's optimizing and having random baloney fucking optimizations that do things that you didn't demand it to, that it shouldn't optimize. No, it just fucking reads it and executes. And pardon my French, but I was really irritated that I had to compile all of my code until I saw this and went, these unneeded steps are fucking excessive. Excuse me for sounding like a sailor once more, but when you have to compile a large project, eventually you start seeing CMake and make files, and then random build documents for things and tools like Ant and Mason that you shouldn't need. You shouldn't need those excessive dependencies just to get one thing to work and bind, regardless of the initial language. Like, this is the part of it where you can bridge anything that's C++ based as a language inside of Python now, in all likelihood. I should know this because I was out looking on the web, and one of the things that I looked for to test if this project even worked was can it use existing C code, namely transpiled from another language like Java. And fun fact, you can. It's a horrible, nasty, evil voodoo thing that you can do. One of the websites is calcicode.com. The other is javainuse.com, and they have a specific transpiler that takes your Java code and throws it into a C-like structure and collection of imports and functionality. What I found is that using a bit of both of these sites, you could, make an actual C program or something that looked like a C program from Java code. The other website I tested this with was Godbolt to see if it would both read and compile and execute. And sure enough, it was type complete enough that yes, you can completely compile down theoretically, or you can annotate from the highest level to a lower level language like C++ that has partially been embedded in Python. And because it's fairly dynamic, it's very useful for things like, intermixing scope. We'll get to that. So one of the benefits is reduced compiling. The other is less need for bindings because you've already got those in an interpreter. Within an interpreter. Terrible dog meme. Didn't care to insert it myself. But I probably should at some point. Moving on. The things that would benefit would be basically not having to compile all of your code over and over and over again. That would get really annoying for anyone who has to develop a browser or, say, X11 bindings, or, anyone who develops a C++ application ever. Now this large headache of, did I structure this correctly? Are all of my imports and files in the right place? Did I have to compile everything? Is it compiled correctly? Did I get a type mismatch and have to recompile everything? Did I have to restructure all of it because part of it's optimized, part of it's not, and did we do proper cleanup? And I said, big F you to all of the compiling and access files and linking step, and said, there has to be a compile once and be done. And now that large headache for most programmers can be removed. The ones who get to enjoy making lots of money off of C++ and whatever programs they write. This includes Java developers and C++ developers, as well as other Python developers. Excuse me if I sound slightly repetitive. The research for this was repetitive and exhaustively annoying, because I personally felt stupid looking for this. So how do I get started? Well, if I were you, I would do it the way I would have done it. You can compile it from PyPy itself. Building the wheel is going to be manual. You might need to have GCC or C++, namely G++, installed. If you're on Windows, I'm sorry, I haven't tested that yet. Good luck. Enjoy WSL or Cygwin or something that's just as functional. I haven't tested that area yet, so I don't know how functional it will be on Windows or on Mac, but it's likely to work with Mac, so enjoy exploring. Any project that you plan on not necessarily compiling anymore, because that's annoying. Compile once and then remove the compiler. And I personally would put it in Docker containers, because it's probably going to be used somewhere in production, if you're using it for production. So, this example, what you see is a couple of annotations. The annotations that are more important are the ones that aren't NumPy related or Numba related. You could probably optimize it to be just-in-time compiled. Either way, it doesn't need to be. Those annotations are optional. That I learned and thought they were manual. The other thing you don't want to mismatch is types by number. And if you do, it's going to expect input there and or have too many inputs, and then it's going to error and yell at you saying that you have too few inputs or too many inputs. And that's going to be kind of interesting, because it'll either be by this cfunc type definition, or it'll be right in the extern C part of the definition for the annotation about the external function. It's a bunch of pointers, and it's really annoying. This is the example for if you still want to use assembly, and this is it compiles down, sort of, but it only compiles the assembly portion, namely the minimum you're going to use for your function. This solution I kind of dislike because it also is execute only and doesn't allow for more permission control. So who knows? And anonymous file creation on disk 2 or 3 times. That's going to eventually, if it's a very large project and you have to use this over and over again, create a lot of bloatware that you don't want there, and does a lot of linking that I don't like, which to me partially is going to count as compiling based on how it works. I know that people probably know how it works. I don't care about how it works on the back end. I just don't need it to be that broken. This is example 3 that I had created. Now, this is the least compiled version of it. It just encodes the assembly for the architecture that it's supposed to run on, and then it just passes it right into C like it's an ordinary function in Python. The only difference is that it's getting passed a pointer to the address of the buffer in this case. And if this were a function itself, you could just raw call that function, meaning you could just use this function and enter any number you want within reason. This is the least compiled state, and yet it still runs and is still likely just as fast. So, why are we optimizing things that we don't need to optimize? Because at this point you might as well optimize for disk size and check for, the types, how many, where you assigned it at that point, and slimming down on those, if you want it to still be fast. Or at least faster. Then you have to use things that memoize functionality, and then that gets weirder and hairier. I left that slide in. The reason why I had asked this is, why not the JVM? Well, my thinking is that you may be able to put portions of the Java virtual machine directly inside Python at this point with the CPPYY compiler, or rather, not compiler, interpreter, excuse me. The reason why I asked also in this slide, why not the JRE code. I was referring to why not just the raw Java runtime environment code, namely the Java code that's supposed to be running in Java, right? That would normally be compiled to Java classes, but instead, what I've done is made it fairly easy to annotate. So, with the two websites I mentioned earlier, calcicode.com and javainuse.com, basically you can put portions of your Java code into it, and it will, as best as it can on each of the sites, transpile to C++. And you'll have to take the bits that come out of that and rework it together manually. So currently, all of this code right here, this initially was a Java class. This initially was this class file. And so everything in this class, between those two websites, had transpiled it into this, what I had told it to. Now this line, this part I added myself because I was going to continue developing my own transpiled version. But my point is that I'm trying to run the raw code that would normally be a Java class inside of Python. And because I get to use two websites like this, namely the calcicode.com and the javainuse.com website, to transpile from that high-level language to a low-level and back out to a high-level language, I can practically say the Java runtime can be interpreted and annotated down. So I've also eliminated that compiler accidentally. Sorry, Java. Sorry, Oracle. Didn't mean to do that. And partially I did, but I didn't mean to be that dick. Sorry. Moving on. The compiler is probably not needed anymore after this. So why not keep a copy of the Windows kernel and a copy of the Linux kernel? And, explore it a little with github1s.com. I ran across that looking at all sorts of code and not being able to figure out where it linked to. And I hated that the most about C++. Whereas with Python and normal GitHub, there was no problem looking for that little function that was existing in some other file, and the same was true for Java for a little while. So this sort of tells that issue to go and fly its own kite. But by the end of the day, why not use a copy of the Windows kernel or a copy of the Linux kernel on whatever machine you wanted at that point, including your cell phone, because you're not really compiling it, and your implementation is going to be your implementation. So you get to define it however you want it to run. Now, well, I'm not one to say this is a horrible feat to do. You can do it that way and not compile any applications at that point. You can just run them, and it'll just run in an uncompiled format. Now, I'm not saying you shouldn't consider platform compatibility, but that should be more of a concern rather than, can we go faster? Can we optimize this? Like, the way you have to optimize is to look at all of your code. If you want it to be fast, you have to look for the things that would make it faster by giving it less to execute and less cumbersome things to execute. If you want it to be formatted for size and speed, you have to know exactly what shape of the instruction you're going to need. If you're using it on the wrong architecture, you're going to find out. You're going to need another tool and have to rebuild. That's going to be annoying. So I'd recommend also using Unicorn Engine with this. And that should partially solve the platform incompatibility there. Now, how would one, say, use this with Android? ARM devices, namely. A copy of Termux and making use of CPPYY system setup for running Ubuntu, and using that setup to, once you've got it running, use this project.